The topic given to us is about building water system and design. First, let's tackle about the building water supply system. So, in a building, water supply system has several parts. Its main parts include the following: building supply number 1, number 2, water meter, number 3, building main, number 4, riser, and number 5, fixture branch. Lastly, number 6 is fixture connection. So we will tackle this one by one in order for us to learn and be familiar on how to build water supply systems and how it works. So first, the building supply. The building supply or water service is a large water supply pipe that carries potable water from the district or city water system or other water source to the building. So building supply is the pipe that connects from the community water supply to the building water supply system. Next is water meter. A water meter is required by most district water supply systems to measure and record the amount of water used. It may be placed in a meter box located in the ground, near the street, or inside the building. So yung water meter, ito yung sinasabi nilang kontador ng bahay. Dito mo makikita kung ilan yung water consumption niyo. Ito po yung tsura ng isang water meter. Next is the building main. The building main is a large pipe that serves as the principal artery of the water supply system. It carries water to the building to the furthest riser. The building main is typically run or located in a basement, in a ceiling, in a crawl space, or below the concrete floor slab. So, building main, ito yung pinaka-pipe na nagsusupply sa building. Just like the human blood vessel called the artery, which pumps blood from the heart to the body. As the same for building main, this is the pipe that carries or supplies water to the whole building. Next is the riser. A riser is a water supply pipe that extends vertically in the building at least 1 story and carries water to fixture branches. It is typically connected to the building main and runs vertically in the walls or pipe chases. So riser is the pipe which supplies different floors of the building. It is connected from the building main. So, as a recap, yung una is the building supply. Next is water meter, then the building main, then next is the riser. Next to the riser is the fixture branch. A fixture branch is a water supply pipe that runs from the riser or main to the fixture being connected. In a water supply system, it is any part of the piping system other than a riser or main pipe. Fixture branch pipes supply the individual plumbing fixture. A fixture branch is usually run in the floor or in the wall beneath the fixtures. So, fixture branch, it is a pipe from riser or directly from the main that connects to the fixtures like toilet, lavatory, bathtub, and other fixtures that has been discussed previously. Sunod naman po ay ang fixture connection. A fixture connection runs from the fixture branch to the fixture. The terminal point of use in a plumbing system, a shut-off valve, is typically located in the hot and cold water supply at the fixture connection. So, may mga oras po na ang isang building ay kailangan ng hot and cold water. So, dito po pumapasok yung shut-off valve. Ginagamit ang shut-off valve para doon. Now, since we already know the main parts of a water supply system, let's now move to the general water distribution system layout. The water service pipe is an underground pipe that is typically called a lateral. The water service lateral is connected to a water meter that measures consumption. If the building plumbing system is served by a well, a water meter is not needed unless monitoring of consumption is required. A water service shut-off valve is typically located at the meter location. As the building supply piping enters the building, pipes is split off to supply water to the hose bibs, the irrigation system, and any industrial process equipment, using water that does not need to be heated. A building shut-off valve is typically located at this location. So this system layout considers that the building needs hot and cold water supply. Once the water enters the lateral, the water is then split up for cold and hot water. Cold water moves directly to hose bibs, while water needed for hot water will move to a boiler or heater. Once the water supply main passes through the softening or treatment device, the main pipe is fixed to provide water to a water heater or water heating system that generates hot water before it is distributed. So, as I said a while ago, a fixture connection links the hot or cold water branch to the fixture. The terminal point of use in a plumbing system. Air chambers are installed as close as possible to the fixture valves or faucets and at the end of the long runs of pipe to reduce water hammer. So later, we will talk about what is air chambers and what is water hammer. In a conventional rigid pipe water distribution method, fixture branches extend from a riser or main to the individual fixture being connected. A fixture branch is usually run in the floor or in the wall behind the fixtures. So, there is two pipe distribution configuration. One is the rigid pipe distribution configuration, and number two is the home run or manifold distribution configuration. So first, let's talk about rigid pipe distribution configuration. In the conventional rigid pipe distribution configuration, the hot and cold water distribution pipes are installed parallel to one another as they convey hot and cold water to risers and branch pipes. A branch supplying water to two or more fixtures is called a zone. A zone can supply one or many fixtures on one floor or on a few floors. Fixtures are typically located in clusters called groups. From the word rigid, the common piping material used here is mostly metal or thermoplastic, and it can also be copper or steel. So here is the basic parts of a residential rigid pipe distribution configuration. If you're going to look closely, here in the left part is where the supply of water starts. It is the city water main. So what is the curb box for? It is for housing the shut-off valve. Pagdating sa water meter, yung water nag-split na sa water supply system. Yung iba napunta na sa hose bibs for cold water, and other water went to the heater for heating and para makaproduce ng hot water. So may dalawang magkaibang pipe for cold and hot water. Yung mga fixtures na kailangan ng cold water is supplied with cold water, and yung ibang kailangan ng hot water is supplied with hot water. This is a rigid pipe distribution configuration kasi ang branch pipe ay nagpa-follow ng straight line. So here's another picture which shows the basic parts of a commercial rigid pipe distribution configuration. So yung kanina is residential rigid pipe, ito naman is commercial. As you can see, the configuration or orientation of the pipes is parallel to each other. The common plumbing chase dito sa part ng restrooms ay kung saan ang pipes ay nalipon. And yan yung ang common plumbing chase. As you look closely, ang mga restroom ay in line with each other. So, ang purpose nito is for easier installation of pipes. Sunod naman, ito naman, pangalawa, home run manifold distribution configuration. A home run or manifold distribution configuration consists of a plastic or metal plumbing manifold and flexible plastic piping. So, kung sa rigid pipe distribution configuration, most pipes is in a straight line. Pero doon, pag kailangan ng bends, gumagamit ng elbow. And pag may intersection naman, gumagamit ng twist. Samantalang dito, sa home run manifold, hindi kailangan ng elbows and knees kasi gumagamit tayo dito ng flexible plastic piping. The manifold serves as a common location from which all the plumbing fixtures are supplied. A water line dedicated to each fixture originates at a port in the manifold and extends to the individual fixture, so fewer fittings are required. Home run configurations typically use cross-linked polyethylene or PEX or composite PEX Altex piping, which is suitable for cold and hot water use. Because of the flexibility of PEX, there is less of a need for piping, tees, and elbows. Yun na nga, yun yung pinagkaiba niya sa rigid pipe distribution configuration. So here is an image that shows home run or manifold distribution configuration. So kada fixture is may specific piping na nakakabit sa manifold. As you can see, parang mas matrabaho to kaysa sa rigid pipe distribution configuration. And hindi rin to practical sa pangmalaking leaking. Pero dito nga ay hindi na kailangan ng mga elbow or knees kasi flexible na sila. Almost the same lang sa process sa rigid pipe. Yung water is from the city water main, then sa curb box, papunta sa water meter. And after sa water meter, makikita natin na pupunta ang tubig sa manifold. So, from the manifold, pakapasok sa manifold, manggagaling naman sa manifold yung mga tubig at pupunta sa kada pipe ng kada fixture. Didistribute from the manifold yung water. So this image is basic parts of a home run manifold distribution configuration. Hot and cold water lines dedicated to each fixture originate at individual ports in the manifold and extend to the individual fixtures. So another picture, close-up picture ng manifold. The manifold of a home run water supply distribution configuration. Water enters the manifold at the bottom. Ito, makikita nyo dyan sa baba. The pipes at the top of the manifold serve and return from the water heater. Flexible pipes run to individual fixtures. So, dun sa mga flexible pipes, makikita, pumapasok dun yung cold water. Yung cold water sa right side and yung hot water naman sa left. Sa taas. You can see Upfeed and Downfeed distribution. These are the two basic types of water supply distribution systems that are used in the building. The Upfeed or upflow system and the Downfeed or downflow systems. In a conventional upfeed system, water pressure from the water supply main is relied on to the direct water flow through the system. Water pressure in building water supply mains typically ranges from 40 to 80 psi, with 80 psi considered the upper limit for most systems plumbed with metal pipe and 40 psi the upper limit for plastic pipe. In tall buildings, water must be supplied through a pump upfeed distribution system. A pump upfeed system is one in which water entering the building flows through pumps that maintain adequate water pressure throughout the structure sufficient to operate any plumbing fixture. So, since sa upfeed system, umaasa lang dito sa water pressure from the water supply main. Yung type ng distribution system na to, hindi siya applicable para sa mga high-rise building kasi di na maaabot ng supply ng tubig yung matataas na floors or palapag. Pero, yung iba gumagamit ng pump para maabot pa din yung ibang mataas na part ng building. Ito po ang image para sa Upfeed distribution. An Upfeed plumbing system supply relies on street pressure to drive water flow. If you look closely, ang tubig ay umabot lamang sa Upfeed pang-apat na palapag. So, hindi na naabot ng pressure ng tubig yung pang-fifth floor. Hanggang dun lang talaga siya sa fourth floor. In buildings that cannot be adequately serviced to the top floor by an Upfeed system, water is pumped to elevated storage tanks in or on the building, and the water is fed down into the building by gravity. This gravity system, fed from the upper stories to the lower, is called a Downfeed distribution system. So, dito sa image, pinapakita yung kombinasyon ng dalawang distribution system, yung Upfeed and Downfeed. Pag sobrang tataas na ng building, gumagamit na sila ng Downfeed distribution system para maabot yung mga nasa pinakataas at pababa ng building. So, sa pinakababa, makikita natin na ang water ay ipapump papunta sa tank na located sa rooftop ng building. And from the tank, magsusupply ito ng water pababa dun sa mga top floors. So this image is a Downfeed plumbing system supply is needed to provide adequate pressure on upper floors. It is usually combined with an Upfeed system that provides water to the lower floors. So meron tayong mga dapat i-consider tungkol sa water pressure. So these are water pressure considerations. First, we have hydrostatic pressure, then water pressure, pressure difference, static head, and lastly, we have pressure losses from friction. Hydrostatic pressure. A hydrostatic force is a force exerted by the weight of the fluid against the walls of a vessel containing the fluid. So, hydrostatic pressure, ito yung dapat i-consider in selecting pipe materials. Kasi ito yung pressure na kailangan i-withstand ng pipe material natin. The hydrostatic pressure, the hydrostatic force per unit area, is perpendicular to the interior walls at every point. If the pressure were not perpendicular, an unbalanced force component would exist in the fluid would flow. If gravity is the only force acting on a fluid, then the hydrostatic pressure at any point in the system is directly proportional to the weight of a vertical column of that water. In other words, the pressure in the liquid increases with depth because of gravity, wherein the liquid at the bottom has to bear the weight of all the liquid above it, as well as the relative air pressure it is exposed to. Here is an image showing the pressure in the liquid increases with depth because of gravity, which is indicated by the flow rate of each nozzle. So you can see the pressure increases with depth, and we have the strongest jet kasi yun sa baba yung mas mataas yung pressure, and the weakest jet kasi mababa yung pressure na dinadala niya. Additionally, the pressure is independent of the size or shape of the container. For example, a 12-feet pipe that is filled with water and is slanted so that the top is only 6 feet above the bottom, measured vertically, will have the same hydrostatic pressure exerted at the bottom of the 6-feet vertical pipe even though the distance along the 12-feet pipe is much longer. The pressure remains the same regardless of the size or shape of the container. Ultimately, the height of the liquid aside from the air pressure is the only factor that matters. So, ito yung example. Para mas maintindihan nyo, nandito yung image. The way we determine the hydrostatic pressure is by this equation. P is equal to Greek letter rho times G times D, where P is the pressure, Greek letter rho is the density of the liquid, G is gravity, which is 9.81 meter per second square, and D is the depth or the vertical distance relative to the liquid surface or highest point. Second is water pressure. Water pressure available at the water service is considered acceptable in the range of 40 to 80 psi, or 275 to 550 kilopascal, or greater in mountainous regions. In most residential and commercial systems, the upper limit is 80 psi or 550 kilopascal, while some systems with thermoplastic supply piping set the upper pressure limit much lower, usually about 40 psi or 275 kilopascal. Residual water pressure is the pressure available at the outlet just before a fixture. Code specifies that the highest or most remote outlet fixture should have a minimum pressure of 8 psi or 55 kilopascal for flush tanks and 15 psi or 103 kilopascal for fixtures with flushometer valves. In the image, this is a table that provides the recommended residual pressures for different plumbing fixture types. We have ordinary basin faucet, 8 psi, self-closing basin faucet, 12 psi, sink faucet, 3/8 inch, 10 psi, sink faucet 1/2 inch, 5 psi, bathtub faucet, 5 psi, laundry tub cup, 1/2 inch, 5 psi, shower, 12 psi, water closet, 15 psi, urinal or lush valve, 15 psi, and lastly, garden hose, 50 feet, and hose bibs seal top, 30 psi.
Pressure difference. The pressure difference, or delta P, is the driving force of a fluid flow. Pressure difference must exist at the plumbing fixture to cause water to flow, that is, water pressure at the fixture must be at a higher level than the atmospheric pressure for water to flow from the fixture. Pressure difference from elevation change. In the building plumbing supply system, water is the fluid under consideration. Water has a maximum specific weight of 62.4 pounds per cubic feet. Therefore, at its maximum weight, a 1 feet cube of water exerts a maximum force of 62.4 pounds at its base, which equates to a pressure of 62.4 pounds per square feet, or 0.433 psi at the base of the cube. Pressure difference from elevation change, or simply static head, is found by multiplying the vertical height z in feet by the factor of 0.433 psi per feet. Pressure difference is negative, and it's a loss if the elevation change from the known pressure is upward, positive z, and positive if elevation change is downward, a negative z. Static head in psi, delta P static is equals to negative 0.433 times the vertical height. In the SI metric units, where vertical height z is measured in meters. So in kilopascal, delta P static is equals to negative 9.8 times the vertical height. So let us try to solve a sample problem. Plumbing fixture outlet is 24 feet above the water service line. Pressure available at the water service is given 45 psi. So let's try first to determine the change in pressure from elevation, and we're going to use the psi unit. So delta P static is equals to negative 0.433 times the vertical height z. Next is to substitute z into 24. So negative 0.433 times times 24 will equal to negative 10.4 psi, which is a negative value, so it means it's a 10.4 psi loss. Change in elevation is upward from the known pressure, so delta P is negative. Let's solve for pressure available at fixture. If we add 45 psi plus the negative 10.4 psi, we will get 34.6 psi. So 34.6 psi is the pressure available at fixture outlet. Pressure losses from friction. In fluid flow, friction loss or skin friction is the loss of pressure or head that occurs in pipe or duct flow due to the effect of the fluid's viscosity near the surface of the pipe or duct. Pressure losses from friction. Friction head delta P friction are more difficult to compute as they are related to flow rate. This pressure drop chart applies to smooth pipes such as copper and plastic pipes and tubing. Pipe diameters range from 3/8 to 1 inch, based on types K, L, and M copper tubing sizes. So, let's refer to the legend in the upper left-hand corner of the chart. Beyond 1 inch diameter tubing, pressure drop disparity with difference in wall thickness is negligible. The pressure drop chart in the figure applies to pressure drops as water flows through a water meter. Water meter design typically reduces pressure significantly. It should not be neglected in pressure drop computations. So, other sources for friction loss, in addition to pipe length, friction loss from fittings and valves must be taken into account. Analysis is usually founded on the equivalent length based on the type of valve or fitting.
Water supply design concerns. Water supply design concerns. Number 1, water velocity. Number 2, cavitation. Number 3, cross connections. Number 4, backflows. Number 5, water hammer. 6, thermal expansion. 7, viscosity. Number 8, volume change with temperature change. Number 9, aging. Number 10, pipe insulation. Number 11, testing, and lastly, leaks. So what is water velocity? While flow rate is the amount of water moving, the velocity is the speed at which the water is moving. So yung water velocity, ito yung bilis ng takbo ng tubig inside the piping material. Noise, erosion of inner pipe holes and valves, and economy of installation, operation, and maintenance dictate the minimum and maximum water velocity in a plumbing system. As a result, these have a bearing on pipe diameter. So, the smaller the area of the pipe, so mas maliit din yung diameter ng pipe, na ibig sabihin ay mas mataas yung water velocity. If pipe diameters are small, cost is low but noise, erosion, and pumping costs are high. In contrast, large diameter pipes reduce noise, erosion, and pumping costs but result in high installation costs. An intermediate pipe diameter is desirable. Typically, plumbing codes set velocity limits, so this plumbing code stated is the International Plumbing Code. Set velocity limits in water supply piping. Maximum water velocities in plumbing water supply piping are usually limited to a range of 5 to 10 feet per second. Ito yung sinet na maximum water velocity ng International Plumbing Code. Next, maximum velocities of up to 15 feet are allowed for equipment feed lines in mechanical rooms. Example, boiler feed lines where noise is less of a concern. Since boiler room naman at hindi siya located sa residential area, okay lang na maingay at allowed yung ganun kataas na water velocity. which is 15 feet per second. The maximum safe velocity for thermoplastic pipe is about 5 feet per second. So next is cavitation. It is a physical phenomenon that occurs in a liquid when it experiences a drastic drop in pressure that causes the liquid to vaporize into small vapor bubbles. Kapag may drop in pressure, ibig sabihin, galing sa positive pressure naging negative ang pressure na nagkakos sa water na mag-evaporate. So, bakit isa sa mga concerns ang cavitation? Because in a plumbing system, as much as possible, dapat hindi ito mapasukan ng gas or ng air. The liquid being vaporized expands quickly, and as the low pressure returns to the normal pressure levels, these bubbles implode as the vapor changes phase back to a liquid and thus drastically decreases its volume. So from vapor, yung mga water bubbles, nag-implode siya. So, kung ang explode palabas, ibang implode papasok. So, nag-implode yung water bubbles into a liquid. This implosion causes noise and high levels of erosion, where the imploding bubbles contact the wall of a pipe, fitting, pump, or valve. So, yung implosion na yun, nagkakos siya ng ingay sa mga pipe. Over time, the erosion results in excessive wear. This eventually manifests itself as pinhole leaking. So, ito yung example ng pinhole leaking. Valves can develop cavitation when they are partially closed and flow is restricted. The result is noise and possible damage from erosion. Cavitation can also develop in a pump, which is noisy, and can adversely affect pump performance by causing violent and damaging vibrations, and a sharp drop in discharge pressure. It occurs if the pump liquid on the suction side of the pump drops below its vapor pressure. Eliminating this potential for cavitation is necessary because a cavitating pump can be completely damaged in a few hours of operation. So, delikado talaga yung cavitation. Number 3 is the cross connections. A cross connection is an unsatisfactory connection or arrangement of piping that can cause non-potable water to enter the potable water system. So this is a vital concern because it can cause danger to one's health. Once yung non-potable water is mainom mo, di ba? Pwede kang magkasakit. A cross connection can cause used or contaminated water to mix with the water supply. It is an unsanitary and potentially hazardous condition. Most plumbing fixtures are designed to prevent a cross-connection. A gap exists between the faucet and the rim of the valve in lavatories, sinks, and tubs to create a separation and avert a cross-connection. An air gap is the vertical distance through open air between an opening in a fixture or faucet conveying potable water to the flood level rim of a tank or As a general rule, the minimum air gaps for cross-connection protection for fixtures against one wall are as follows. So this is measured from the opening of leaves or faucet to the flood level of rim. For lavatory, 1 inch. For sink, 1.5 inch, and the same as the laundry tray, 1.5 inch, and in bathtub, 2 inch. Next is backflow. Backflow is a type of cross-connection that occurs when contaminated water or some other liquid or substance unintentionally flows backward into distribution pipes containing potable water. So this is equal dangerous as to the cross-connection. So both of it must be avoided. Simply, it is water flowing in the opposite direction from normal flow. Backflow can allow contaminants to enter the potable drinking water system through cross-connections. A backflow can be a serious plumbing problem that can cause illness and even death. Back pressure or back siphoning is backflow caused by a negative pressure in the potable water system. A downstream pressure that is greater than the supply pressure causes back pressure backflow. A backflow prevention device, often called a vacuum breaker, is a device or plumbing assembly that, when properly installed in a plumbing system, prevents backflow. Number 1. The atmospheric vacuum breaker, or AVB. The most common type consists of a body, a check valve-like member to prevent backflow, and an atmospheric opening. So here how it looks. This is a 1-inch brass atmospheric vacuum breaker mounted on PVC pipe. So here is the actual atmospheric vacuum breaker. Number 2, a pressure vacuum breaker, PVB, is a type of backflow prevention device used to keep non-potable water from entering the water supply. PVB devices are generally required on small residential-sized irrigation systems to keep water contaminated with pesticides and fertilizers from re-entering the building's plumbing system through the irrigation system. So, ganito po yung pressure vacuum breaker. Number 3, a double check assembly or DCA or double check valve is a backflow prevention device assembly that consists of 2 check valves assembled in series, usually with a ball valve or gate valve installed at each end for isolation and testing. So ito po. This is a double check assembly. It's a backflow prevention device that consists of 2 check valves assembled in series. The DCA shown is for the water supply to a fire sprinkler system. Next is water hammer. Water hammer was tackled a while ago in the first topic. So a water hammer. In plumbing supply system, the sudden closing of a valve will cause fast-flowing water to stop quickly, resulting in a large increase in pressure that is known as water hammer. As a minimum, water hammer produces a force that makes pipes rattle with banging or thumping sounds as they expand and contract from exposure to an increase in water pressure. In extreme cases, when the water flow rate is high and the valve is closed very rapidly, hammer can cause a valve to rupture and the pipe falls to burst. So water hammer, ito yung pag sinalang bigla yung piping, yung plumbing system. Yung nag-flow na water biglang may stop, so yung pressure na babalik din sa piping, yun yung magkakos ng water hammer. So, to resolve water hammer, to avert water hammer damage to a building's plumbing system, air chambers or water hammer arrestors are used in the supply branches serving each fixture. These devices use trapped air to cushion the hydraulic shock. So, this is how hammer arrestor looks. A cross-section view of a water hammer arrestor, a patented device to absorb hydraulic shock. Next is thermal expansion. The amount of expansion will depend on the type of piping material and the range of temperatures that the pipe will be subjected. This is particularly important because the most commonly used material in plumbing is copper pipe, which is highly subjected to thermal expansion. Thermal expansion in the pipes of a plumbing system must be accommodated to minimize damage from thermal movement. Expansion from temperature increases can push a pipe through a wall or cause it to burst. So to resolve thermal expansion, expansion bends and expansion loops make use of pipe fabricated with U-shaped or circular bends. The increase in the length of pipe from thermal expansion is accommodated by flexing or springing of the bends or loops. So in the figure, these are the types of expansion vents and loops. Another is expansion joints. Expansion joints in common use include the slip expansion joint and the corrugated expansion joint. So in this picture shows a slip expansion joint. The slip expansion joint consists of a slip pipe and a flange which is bolted to an adjoining pipe. Next is the corrugated expansion joint. This consists of a flexible corrugated section. The corrugated accordion-like section is able to absorb a certain amount of end movement of the pipe. So itong paikot na to is the corrugated or the accordion-like section. Makikita nyo dito sa picture. Next is viscosity. As water flows through a pipe, its viscosity or thickness decreases with temperature decrease. Water at 40°F is twice as viscous as water at 90°F and 4 times as much as 170°F. As a result, pumping energy and costs are higher when water temperatures are low. Next is volume change with temperature change. We have three types of volume change with temperature change. Number 1 is freezing. Freezing is a phase change from liquid water to solid ice. Results in about a 10% increase in volume. So, nag-change yung temperature, nag-increase din yung volume niya ng water. A pipe fitting or tank filled with water can burst if the water is exposed to below freezing temperature, even for a short period of time. So, delikado din yung volume change with temperature change kasi pwedeng mag-burst yung water. And a burst pipe will typically result in flooding that can cause catastrophic damage to the building and its contents. In most climates, provisions must be made in plumbing system design to ensure that pipes containing water do not freeze. Pipes must be located in a heated space or underground where they are not exposed to freezing temperatures. Number 2, expanding water. So, ito naman yung uso sa Pilipinas kasi nga mainit dito. Expanding water. Liquid water expands above 39°F. Expansion is about 4.37% from 40°F to 212°F. In any piping system, provisions for expansion and contraction of liquid water must be considered. In an open plumbing system such as a building water supply system, pressure build-up from thermal expansion of water is released each time a faucet or valve opens. Excess pressure is released into the surrounding air. Expansion tanks installed in a closed system provide additional volume in the closed system for expansion of water from temperature increase. Number 3 is steam. Although steam is not found in building plumbing systems under ordinary conditions, a faulty water heating appliance such as a boiler or domestic water heater may result in the development of steam. For example, a water heater with defective thermostatic controls, which can have catastrophic results. So, these concerns must be avoided in order for our safety to be ensured. Next is aging. The effects of aging in a plumbing system are related to piping material, quality of water, and water temperature. Build-up from calcium deposits and corrosion reduces the inside opening in the pipe, which restricts flow. Over several decades of use, aging galvanized steel and iron pipe can result in a capacity loss of up to 80%. Copper piping experiences about half the capacity loss from aging as do steel and iron pipes. Plastic pipes experience little loss of capacity as they age. So, aging, pag tumatanda o tumatagal na yung ginamit na materyales, merong pagkakaiba nung bago pa lang siya, nung matagal na siya kasi lumiliit yung capacity ng material. Next is pipe insulation. Pipe insulation is applied to the outer walls of piping to reduce heat loss from the pipe or prevent condensation on the outside pipe walls. Foam and covered fiberglass insulation are common pipe insulation materials. So, ito yung example. Foam, fiberglass, and merong isa, elastomeric foam. Foam din. Hot water supply lines, especially on hot water recirculating systems, should be insulated to reduce heat loss and save energy. In residential applications, in temperate to cold climates, insulating hot water lines is less cost-effective because heat loss from hot water pipes contributes to space heating during the heating season. That is, the heat loss is extremely small. Under high humidity conditions, it is necessary to insulate cold water lines to keep condensation from forming. Next is testing. The water supply system should be tested for leaks before it is covered with finished materials to determine if it is watertight. Tests commonly run on water system require that it be watertight under a hydrostatic water pressure of 125 psi for a minimum of 1 hour. Any leaks that occur should be repaired with the joint compound originally. So testing is a constraint para malaman agad kung may problema ba sa plumbing system. Leaks. Plumbing leaks contribute significantly to water consumption in operating plumbing system. Leaks not only waste money and water, they can cause damage to walls, flooring, ceilings, furniture, and electrical systems. Leaks can develop from substandard piping, improper use of materials, poor workmanship, and improper design. So, itong leaks is pinaka-common na problema sa plumbing system na dapat nating matulungan.
Water supply pipe design methods. Before discussing the methods, we will be first discussing flow rates, water consumption, and water demand. So, flow rates is the speed at which water flows through a pipe. This will vary by the type of fixture and water pressure at the fixture. Each fixture in the plumbing system is designed to operate a specific flow rate, expressed in gallons per minute, liter per second, or liter per minute of flow. Table 13.5 shows approximate flow rates and typical consumption by type of plumbing fixture and location. Flow rates vary significantly by residual pressure. So as you can see at the table, there are different flow rates in different types of fixture. For example, the bathtub faucet has 4 to 8 gallons per minute, while the clothes washer or the laundry has 3 to 5 gallons per minute. And by the way, the residual pressure is the water pressure available at the outlet before the fixture. It affects the flow rates of a fixture. A higher residual pressure results in a greater flow rates and thus more water consumption. Next is water consumption. Water consumption is the amount of water that is taken or withdrawn from the source. About midnight to 5 a.m., water consumption is averaging less than 1 gallon per person per hour. So, ito yung time na sobrang kukunti lang yung water consumption sa bawat bahay. And then, around 6 a.m., it became 3 gallons per person per hour, and during day, water use drops off and rise again early in the evening. In addition, weekly peak flows may occur in some homes on weekends. Kaya weekends nagkakaroon ng peak flows kasi karamihan ng bahay kapag weekends nandoon yung mga adults na nagtatrabaho during weekdays. So mas marami yung consumption during weekends kesa weekdays. However, peak flows at retail store occurs during business hours, and at restaurants, peak flows occur during mealtime. Rental properties, resorts, and commercial establishments in tourist areas have flow rates that vary by season. Table 13.6 contains approximate water requirements for selected buildings. Sa table na ito, makikita natin ng iba't ibang type of buildings kung saan meron din silang iba't ibang flow rates and demand loads. For example, yung hospital, kapag meron itong 0 to 50 number of fixture, may flow rates ito na 1.0 gallon per minute. At yung maximum capacity naman niya is 50 gallon per minute at ang minimum capacity ay 25 gallon per minute. At yung values sa table na ito, based siya dun sa equal number of men and women occupants. At kapag majority ng occupants are women, nag-i-increase yung capacity by 15%. Water demand. The amount of water required for a given purpose. The instantaneous peak demand for water in a pipe serving a number of plumbing fixtures or serving an entire building is referred to as design loads. Design loads is the maximum probable or peak instantaneous demand for domestic water by a group of fixtures. Design loads of a pipe serving a group of plumbing fixtures will depend not only on the number and type of fixtures installed, but on the operation of the fixtures. So let's now move on to domestic water by a group of fixtures. Design loads of a pipe serving a group of plumbing fixtures will depend not only on the number and type of fixtures installed, but on the operation of the fixtures. So let's now move on to the main topic, the water supply pipe design methods. We have 4 methods. Method 1 is simple empirical design method. Method 2 is the WSFU or the water supply fixture unit design table method. And method 3 is the velocity design method. And method 4 is the equal friction design method. Method 1. Simple empirical design method. In the empirical design method, piping is sized with rules of thumb based on the observation and experience. For example, the mains that serve fixture branches can be sized as follows. Up to 3 1/2 inch branches can be served by 3/4 inch main. Up to 3 3/4 inch branches or up to 6 1/2 inch branches can be served by a 1 inch main. Up to 5 3/4 inch branches or up to 10 1/2 inch branches can be served by a 1 1/4 inch main. The empirical approach is used in the design plumbing system for residents and similar building with simple plumbing system. Branch pipes can be sized from minimum branch requirements cited in the building code, such as those provided in Table 13.7. So here in table 13.7, supply branch size and water supply fixture unit load requirements of common plumbing fixtures is shown. So, in this table, there are different types of plumbing fixtures and it has a corresponding minimum branch pipe size. And of course, a water supply fixture unit load, or the WSFU. The second method is WSFU design table method, and WSFU stands for Water Supply Fixture Unit. To do this method, we have to follow the following steps. First is to obtain the minimum service water pressure for the location of construction. Usually, this is available through the municipal water department. And then next, compute the total WSFUs, including proposed and projected future plumbing fixture. 3. Calculate the maximum developed length of water piping, the actual length of pipe between the source of supply and the most remote fixture plus the developed length of fittings. Developed length can be approximated by multiplying the actual length to the most remote fixtures by 1.2 to compensate for the loss of meter and fittings. Next, compute the static head and subtract it from the service water pressure. Then, use table 13.10 to determine the water and distribution pipe sizing based on the total demand in WSFUs, maximum developed length of water piping, and the supply pressure. Ito naman yung table 13.5 na tinutukoy dun sa step 5 kung saan dito titignan yung sizing ng pipe at saka yung length. So we have sample problem here. Using the WSFU design table method, determine the minimum meter and distribution pipe sizes. Assume the following. Minimum service water pressure for the location is 65 psi. Total WSFUs is 28. Actual length of the pipe between the source of supply and the most remote fixture is 83 feet. And the elevation above the source of supply is 23 feet. So first, we have to obtain the minimum service water pressure for the location of construction. In this problem, given naman siya, so we have 65 psi. And then, step 2 is to compute the total WSFUs. And we have 28 in this problem, given siya. At kapag hindi siya given, makikita natin to dun sa table 13.7, yung pinakita ko kanina. And then, step 3 is to calculate the maximum length of the water pipe. So, we have here in 83 feet actual length of pipe. I-multiply lang natin siya sa 1.2 based dun sa step 3. And then, makakakuha na tayo ng 99.6 feet, which is approximately 100 feet. And then, step 4 is to compute the static head and subtract it from the water service. So, para makuha natin yung static head, gagamitin lang natin yung formula niya. So, negative 0.433, i-multiply lang natin siya dun sa elevation, which is 23 feet. At makakakuha na tayo ng negative 9.96 psi or approximately negative 10 psi. And then, para ma-obtain naman natin yung supply pressure, isa-subtract lang natin yung nakuha nating static head dun sa service water pressure. So, 65 psi minus 10 psi is equals to 55 psi. And then, yung last steps, gagamitin natin yung table 13.10, yung pinakita ko kanina. At iti-trace lang natin doon gamit itong mga information na na-compute natin. And by looking at the table, yung makuha nating meter and street service pipe size is 3/4 inch and the building supply and branch pipe size is 1 inch. Moving on to the third method, the velocity design method. The velocity design method entails selecting the smallest pipe diameter without exceeding a pre-established maximum velocity for the design loads in the pipe. The procedure is outlined below. First, sum the total number of SFUs for hot water and cold water. Then, determine the maximum probable demand in gallon per minute. Then, based on the maximum desired velocity and design loads, solve the minimum required diameter. And then select the pipe size for the appropriate pipe material with an inside diameter equal to or greater than the minimum required diameter. So we have a sample problem here. A large 10-story office building has a demand load of 60 WSFU for cold water and 25 WSFU for hot water at each floor. An additional supply of 18 gallons per minute of cold water is required in the basement for make-up water, for mechanical equipment, and landscaping sprinkler system. The system will be plumbed by type L copper tube. Use the velocity design method to determine the minimum required size of hot and cold water supply pipes serving the building based on a maximum velocity of 8 feet per second. So first, we have to get the total cold water demand load. So we have to multiply the 60 WSFU by 10 stores and we will get 600 WSFU. Tapos, titignan natin sa table 13.9. Papakita ko mamaya. Titignan natin doon yung 600 WSFU. And then, doon sa table, yung 600 WSFU is equal to 100 GPM. And then, itong 100 GPM, i-add lang natin dito yung additional supply, which is 18 GPM. Kaya magkakaroon tayo ng 118 GPM or yung design loads. And then, using the formula for the minimum diameter, the square root of 0.409 times Q over V. So, isa-substitute lang natin yung mga value. Sa Q yung 118 GPM at sa velocity naman ay yung 8 feet per second. And then, solve natin sa calcu at makukuha natin yung 2.46 inch diameter. And then, sabi dun sa last steps, select a pipe size for the appropriate pipe material with an inside diameter equal or greater than the minimum required diameter. So using the table 12.9 from chapter 12, a 2.5 diameter type L copper tube with an inside diameter of 2.465 inch is acceptable. So, ayun yung sa cold water. Tapos, yung sa hot water naman, the total hot water demand load is 25 WSFU times 10 floors. So, we have 250 WSFU. At kung titignan natin ulit dun sa table, makikita natin na equal to dun sa 76 GPM. And using the formula for the minimum diameter, isa-substitute lang natin yung value, and then pag sinolve natin, makukuha natin ay 1.971 inch diameter. At according ulit dun sa table 12.9 in chapter 12, a 2-inch diameter type L copper tube with an inside diameter of 1.985 inch is acceptable. Tapos, dito naman sa letter B, use the velocity design method to determine the minimum required size of the main supply pipe serving the building based on the maximum velocity of 8 feet per second. So, yung solution dito para sa letter B, total demand load for hot and cold water is equals to 600 WSFU plus 250 WSFU dun sa na-compute natin kanina. Magkakaroon tayo ng 850 WSFU, which is equal naman siya sa 117 GPM na based ulit dun sa table 13.9. And then, itong 117 GPM, i-add natin yung additional supply na 18 GPM at makukuha natin ay 135 GPM. And then, gagamitin ulit natin yung formula para sa minimum. The square root of 0.409 times Q over V. And then, substitute lang natin yung mga values. Tapos, makukuha natin ay 2.627. And then, based ulit dun sa table 12.9 in chapter 12, a 3-inch diameter type L copper tube with an inside diameter of 2.627 inch is acceptable. Ito naman yung table 13.9 na tinutukoy ko dun kanina kung saan nanggaling yung equivalent ng WSFU na GPM. So, this is table 12.9 from chapter 12 kung saan nanggaling yung final answer natin dun sa sample problem. The fourth method is the equal friction design method, a more accurate approach to sizing the pipe diameter in a complex network of pipes is the equal friction design method. To do this method, first, we have to find the volumetric flow rates along the side of the chart. Then, move horizontally across the chart to the pipe diameters and for specific nominal diameters. Note associated pressure drops and velocities. Then, select a pipe diameter having the desired pressure drop including fittings without exceeding the velocity limitation requirements. So let's have an example. Select a nominal pipe diameter of copper pipe type L with a volumetric flow rate of 100 GPM. The desired pressure drop from friction loss is 6 psi in 48 feet. Use a 50% increase in pressure drop from feeding losses. So, may data na tayo dito. Galing ito dun sa friction chart na ipapakita ko sa next slide. And then, yung gagawin lang natin is i-compute natin dito yung friction loss kada pipe or sa bawat iba't ibang diameter ng pipe, and then yung may pinakamalapit doon sa desired pressure drop, yun yung magiging final answer. So, first, the 4-inch pipe, 0.27 psi per 100 feet siya, and then i-multiply lang natin yung 48 feet, and then times 150% since 50% increase in pressure drop yung sa feeding losses natin. And then magkakaroon tayo ng 0.19 psi, and then compute natin yung sa 3.5-inch pipe, pati na rin yung 3-inch pipe, 3.5-inch pipe, and 2-inch pipe, and 1.5-inch pipe. And then, after makompute nitong lahat, ito na yung computation. Yung may pinakamalapit na sagot ay yung 2-inch pipe. So, the pipe with a 2-inch nominal diameter has a pressure drop from friction loss that is closest to the 6 psi. So, yun yung magiging, or yun yung pipiliin nating nominal pipe diameter. Yung sabi ko, friction chart kung saan nanggaling yung data on sa sample problem.
Our next topic, it will be the water temperature. Water is essential in our living, and different temperature of water is for our different necessities. For this topic, 4 temperatures will be discussed: the cold water, the chilled water, the heated water, and the tempered water. So for the first one, water. In a moderate climate, cold water may range to 35 degrees Fahrenheit to 70 degrees Fahrenheit, or 2 degrees Celsius to 21 degrees Celsius in midwinter. In a hot climate region, such as in the Africa and the Middle East Asia, the water surface temperature can reach above 90 degrees or 33 degrees Celsius or more in summer due to the extreme hot weather conditions. Water. Chilled water is a commodity often used to cool a building's air and equipment, especially in situations where many individual rooms must be controlled separately, such as a hotel. For some people, they prefer the chilled water as their drinking water because it is more refreshing. A chiller is used to cool water to a temperature of about 50 degrees Fahrenheit or 10 degrees Celsius before it is used. In a modern building, hot water is desired for bathing, cleaning, washing, and other associated purposes. In a country that experiences winter season, hot water is needed for their bath because it is needed. By definition, hot water is a potable water that is heated to at least 120 degrees Fahrenheit. Next one is the tempered water. Tempered water is a blend of hot and cold water that is mixed at a thermostatic mixing valve. A thermostatic mixing valve is a valve that blends hot water with cold water to ensure constant safe shower and bath outlet temperatures, preventing scalding. Tempered water is used in applications requiring low temperature hot water. The typical application of tempered water includes shower rooms, roof showers, domestic water for small buildings, and temporary water for light industrial processes. For example, the photographic laboratories.
That is our topic for now. If you have any question, comment it down below.